work. So we are on chapter, let's see where we are. We left off talking about analysis of variance for simple regression. Okay? So we're doing this partitioning the total variability of the y's into two pieces, one due to the model and one due to the error. And if we wanted to do this from scratch, we did it with 3 points, and you did it on your homework this way, but that takes a long time to do. Look how long it takes with just 3 points. Now we have data that has 107 points, and we don't want to do this. So I said a very cool, handy way to think about this that helps you know what's going on is to use R squared. And R is included on almost all regression analysis. And R, right here, is little, for simple regression, little r and capital R are the same thing, except capital R is always positive. So this is a handy way to do the same partitioning because what? The sum of squares model, we said, is R squared times the sum of squares total. This sum of squares total, which is just the deviations from the y-average squared and summed up, right? It's n, it's just, that's what it is. It's just n times your standard deviation of y squared. Okay, so in this case, it would be what? This is y. You're predicting finals from homework, and we've got these 5 summary statistics, and we have a sample size of 107, and we're trying to predict what from a much larger class, 2,000. Whether there's some, all we're looking at is we're going to predict whether this correlation coefficient is different than 0. The null says that rho, or Greek R for correlation, or R for the population, is 0, that there's no correlation between homework and finals. That's kind of ridiculous, but that's what this test would do. We know there probably is. We got a correlation of 0.4. So the question is, how likely would that be just be due to the luck of the draw? That's what a significance test tells us. That if there was no correlation, how likely would we see to get a sample that was that far from 0 just by the luck of the draw? All right, so we're testing against the alternative that rho is not 0. We assume that rho is 0 and compute how likely it would be to get a sample R as far away from 0 as we got just by the luck of the draw. Okay? And this is the same thing. When R is 0, beta, your slope's 0. So it's exactly the same thing as testing whether the slope is 0. All right. So here's our model. So we're testing whether this slope is 0. All right. So we're going to use, instead of doing it the long way with 107 points, we are going to partition this variability of the y's. What is this? This would be n is 107 times 10.3 squared. We are going to have a calculator. Hold up. I don't know what I did with it. Shoot, that's too bad. Okay, I wrote it down last time, so I can tell you what I got. Okay, so I got 11,351.63. Okay, so that is down here. That's our sum of squares total. And we're going to partition this into 2 parts. What's R squared? That's 0.4 squared, so that's 16% of that. 0.16 times that, 16% will be here. And when I took 16% of that, 0.06 times that, I got, thank you. You get an extra credit point. Now, if you know what, you could do it an easy way. You could just subtract that from that, or you could say 0.84 times this. because this is r squared, so 1 minus r squared is going to be 0.84. So take 0.84 times that. Could you do that for me? 9,500 and what? 0.37. Yay, thank you. Okay, so everybody knows that now. Degrees of freedom. Let's do our degrees of freedom. And our degrees of freedom are going to be what? Do you remember what they're going to be for the total? That's n minus 1, right? So that's 107. We talked about that last time, so that's 106. And then these, the degrees of freedom for the error. Remember that each one of these, the error is the error off the regression line for each point. And there are 2 points determine a line, so we subtract the first 2 off, and we have 107 minus 2, which is 105, which means this one has to be 1, because 1 plus 105 adds up to 106. This plus this adds up to that, all right? And this was for our model, which was the number of parameters, 2 parameters. What are parameters? Parameters are these betas here. Parameters are to the population what statistics are to the sample. It's what we're trying to estimate. We're trying to estimate. We know we have this model that's a line. Y is equal to our predicted y, which is the final, is equal to some intercept plus a slope times our x, which is our homework scores, right? And so these, we solve for these 2 in our sample, and those are our estimates for our population parameters. So this is n minus 1, this is n minus 2, n minus p in general, and this is p minus 1, 2 minus 1. In other words, all we really care about in this is how y varies with x. This intercept doesn't really matter. So it's always the number of x's in your model. We're going to be adding another x shortly. In a few minutes, we're going to look at a model that has 2 x's in it. For example, this isn't what we're going to do, but let's say we wanted to predict finals from homework and exams, then our parameters would be 3 parameters, 3 minus 1, and we'd have 2 in our model. All right, so we've got this. Now what do? Mean square. So we divide this by 1. So that gives us 1816.26 divided by 1. And I'm going to have to call in your help again. We're going to divide this, 9535.37, divided by 105. Actually, I can read my handwriting here. I got 90.813 for that. So that's, look, it's the mean of the sum of the squares. Here's your sum of squares. You divide them by the degrees of freedom, and there's your means. There's your mean sum squares. Any questions on that? Now, what's the F ratio? The F ratio, or the F stat, is the ratio between the mean square for your model divided by the mean square for your error. And that I did, and I got 20. Okay? Now, some of you can see, and we talked about it last time, that when we're doing this, what are we doing? We have r squared over SST, and this is 1 minus r squared times SST. So when we're doing this, we can just get the F ratio here. When we're doing this, we have r squared over 1 minus r squared times SST over the degrees of freedom, right, which is, in this case, 1. And that's our mean square right here for the model. And then we have 1 minus r squared times SST over its degrees of freedom, right? And so do you see how that cancels out? And what we have is this really nice statistic. I'll say it's the same as up here. It's just what? The same as r squared over 1 minus r squared times 105. So instead of doing this rigmarole, we could have just jumped to the chase and done this. And we get 20 as well. We'll get the same thing, so you can check it that way. So once you know the R squared, it's very nice. And let's look on the next page just for a moment. And this is a summary of the statistics that we've done so far for simple regression. And you can see that what we're doing when we do the F is just a square of the T. And the chi-squared is just a square of the Z. And the numerator is a measure of the strength of our model, and the denominator is a measure of the strength of our errors. And the bigger R squared is, our correlation coefficient, the stronger our model is, and the bigger our sample size is, N, for the same R, the stronger our model is. You know, bigger sample size is going to give you a signal coming from a bigger sample size is more significant. So that's the idea. Now, we've got this 20, and a lot of you aren't used to looking at what does it mean? What is this test at? So our F, what's our conclusion? So we've got this F stat here equal to 20. Now that's a big F stat, all right? How do you know that? Remember we said the mean of F is, when the null is true, is around 1. That's a lot bigger than 1, but we are going to compare it to, we can compare it to the critical value of F when the null is true at some significance level. Let's say at alpha equals, let's say 5%, 0.05. But which F curve? Well, the one that has degrees of freedom in the numerator up here, even though when we simplify it, it turns into the denominator here, but in the numerator of 1, and in the denominator of 105. For the errors, each point has an error associated with it, but the first two don't count because they first 2 points determine a line. So that's in your errors, okay? And we're going to compare it to that, and that is equal to, let's get this out of the way, and that is equal to 4. I looked it up, around 4. We can look it up exactly in a minute. I can't look it up on this table, can I? Let me see if I can. Here's degree of freedom 1, 105. Oh, I see where I got the 4 from. I just said, okay, it's somewhere between 4 and 3.92. I'm just going to be conservative here and estimate around 4. Just by looking here that 107 is in there. If I wanted to find it out more exactly, I'd have to go online. All right? But this is so much bigger than that. Here, let's go online and see. I'm going to show you what we're doing here. All right, so here's our p-value calculator, and I put in 1 degree of freedom, we're on the F distribution, 105 for the denominator, a p-value of 0.05, and it's not quite 4, it's 3.932. But what this means is that this is the distribution of that F statistic when the null is true. Yes?
I just want to know, like, so for the exam, how do we calculate this when we can't use this calculator? Like for the homework last night, I was using the calculator, but you won't have that.
Yeah, good question. So her question is, how would you know it was this? 3.932, you wouldn't. You could estimate it was around 4 from what I just showed you. And since you, look at this. This means, this is how that, when the null's true, which means when the correlation between homework and final is 0, and you compute this, it's possible you could get a really, just by the luck of the draw, go way out and get this big F stat. But this is the, you'd expect to get something around 1, right? And this is the probability, 5%, that you're going to get an F stat bigger than 4. Well, ours is 20. So can you imagine going all the way 4, 5, 6, 7, 8, 9, 10, 11, all the way? I don't even think it would fit on here, but let's say it was here. Now this curve goes on forever. it would be a speck. Let's see what it is. What would be our p-value? It's tiny. If we got 20 in here, let's see, our p-value is that. Tiny, tiny, tiny p-value. Okay? And it's just that tiny. Okay? Does that make sense? Does that make sense? All right. So let's write that down. And the idea is these critical values, just to show you, is this critical value. You draw, there's some curve now. Remember, f is always positive, and we just saw it. It looks something like this. It keeps going, going, going. And they said, okay, at 4, this is our critical value. This is 4. And this is for the particular f curve that has 1 degree of freedom in the numerator and 105 in the denominator. Each curve looks different. So this right here, they say is 5%. That's our cutoff. And we say, okay, but RF, we want to compare RF of 20. RF of 20 is off the paper here. And so our p-value is going to be tiny. RF of 20 is way here. So the probability of getting a stat this big or more extreme, 21, 22, more extreme, higher, by the luck, when the null's true, is tiny. We saw what that probability is. So since 20 is much bigger than 4, okay, our p-value is much smaller than what? 5%. So we reject the null. We say the probability, if the null is true, this is so unlikely. So we're going to say, hey, this probably isn't true. This can't, if the null is true, it's beyond a reasonable doubt, right? Like we'd be getting DNA evidence on a person, the chance, so much evidence, and we'd say, okay, yeah, he still could, there's a tiny chance he's innocent, but we're going to convict. So that's the idea. So we reject the null, and conclude what? Conclude that rho is not equal to 0, or that same as our slope for the homework is not equal to 0. Okay? Does that make sense? Any questions? These significance tests are all done the same way. So you're just going to get, you just have to assume nothing's going on, and then you look at what, you get some test statistic under the, and you can calculate what the probability is of getting that under the null. And if it's too tiny, getting that extreme a value away from your hypothesized null value, if it's too small a p-value, then you say reject the null. Let's do the same thing with chi-squared. So the chi-squared stat, now people don't do this analysis of variance typically with the chi-square stat. It's just, they just calculate it, and this would be r squared over 1 minus r squared times what? N. So in this case, we're doing the same thing, this, right? But instead of multiplying by 105, like we did here, what are we going to multiply by? 107. So it's going to come out a little bit bigger, 20.38. And now we're going to compare this to what? Let's compare our statistic, compare the stat we got from our sample, which is equal to, compare our stat, we'll call it our test statistic, and that was equal to this, to a critical value of chi-squared, so we'll put a little star for critical value. Now chi-square has different curves, but they just correspond to how many, your model. They just are p minus 1. So this is the same as this. It's the same as degrees of freedom 1. It's the same as this. It's the same as one slope. Those are all the same. And it has nothing, you don't even worry about the sample size. Remember, chi-square and n you use when you have big sample sizes. All right, so we're going to compare that to the critical value. And this we probably can look up because look, it just has 1 degree of freedom, so that'll be easy to look up. So let's look in our back of our book. And whoops, 1 degree of freedom for, whoops, that's the chi-square. So it's the next to last page. And you have 1 degree of freedom here. And now at 5%, it's 3.84. So that means if our statistic, let's say that's at 3.84, pretend that was 3.84 and that's 5%, well, anything bigger than that's going to be less than 5% in the tail. So, all right. So let's write that down. And we got something way bigger than that. So we're going to compare that to what we just saw, and that was 3.84. 3.84. 3.84. Okay. Whoops, I didn't say at alpha equals, I have to say at alpha equals 0.05% because it's different. You know, the smaller you make that, the bigger you have to make your critical value. All right. So now, since 20.38 is much, much bigger than that, our p-value is much, much smaller than 5%. Any questions on that?
So the F distribution and the chi-square distribution is always one-sided?
Always one-sided, because can you ever get a negative chi-square? Could you ever get a negative f? They're based on sums of squares. They're based on r squares. Can this ever be negative? No. So that means, and it's the square of the z, is this one. So if you get all the negative z's are going to change to positive, right? Chi-square is this, okay. So with chi-square with 1 degree of freedom is exactly like if we took our t distribution, our z distribution, 0, and if we squared it. So this is z, and chi-square is just z squared. So let's try it and see what we get. So this is 1, this is 2, this is 3. Now, what you do is if you took this, all these, and squared them, what do you get? So if you square 0, you get 0. If anything negative, you're going to get positive. Anything between here, let's say it was 0.5. You square it, you're going to get 0.25. So you're going to get a pile up. It's going to look like this. You can't get a negative. Everything in between 1 and negative 1 is going to get smaller. So negative 1 squared is 1. Positive 1 squared is 1. And everything between here, let's say like a half. If you have a half and you have negative 1/2, they're both going to be a quarter. They're both going to change to a quarter. So you're going to get this pile up like that. Do you see? And now these are going to get all spread out. 2 is going to change to 4, and so is negative 2, right? So you're going to get all spread out like that. That's going to be your z squared, which is your chi-squared. It is really just the square of the z. Does that make sense?
That's the graph of chi-square?
Yeah, but it's a terrible graph. Let's look at it. I mean, you should convince yourself by going here, and let's do it. So let's look at chi-square with 1 degree of freedom. All right, and you can see what it looks like. Oh, I don't know. Let's say you got a chi-square of 2. We can compute the p-value. We can look at it. So there's chi-square. I didn't make it very nice, but I tried to make it. Look at the picture. There's my picture. And here is what it really looks like. How about if I put a 1 in here? Maybe that will look it better. picture's not terrible, but it's not great. But you understand? Of course, if you have more degrees of freedom, it's going to start looking more like the normal curve. Okay? All right, so now let's go back to the document camera. And by the way, the f is the square of the t. So yes, you can only get positive values, and you can see that in the statistics. So you've got 4 test statistics that all test the same thing. Whether you have, for a simple regression, just a line, 1x predicting y, they are all testing whether the slope is 0 or not. Which one to use when? For small n, the t and f give somewhat more accurate values. Remember how the t, you use t when you have smaller samples, and that when you get bigger samples, they're going to be about the same? That's the same with the chi-square and the z. I mean, this chi-squared and the f. They'll give about the same values. For large n, for small n, it's better to use the f. Now, do you want to use z and t or their squares? Well, it really doesn't matter, except as long as you keep in mind that the chi-square and f tests are always positive. So they can only specify a non-directional alternative. They can't distinguish between a negative correlation coefficient and a positive because you're squaring it. So they're all lumped together. So if you want to change it to a one-sided alternative, you'd have to divide the p-value you get by half. And that's what I say here. So the p-value for the chi-square with 1 is the same as for a two-tailed z-test. So that's pretty much the idea here. And to find the p-values for z and t, you have to look at the area of one tail for one-sided alternative, or both tails for two-sided alternative. And same here. That's the same thing, depending on the alternative. That says depending on the alternative. All right, so now, any questions so far? All right, so let's go to multiple regression. Oh, not yet. I can't urge you enough to please read on your own, because no matter how many times I say something and all the concepts, it's just very hard to get it just from listening to somebody. You have to do a lot of practice, and you have to read. So please read what I wrote here about the f-stat, because we are going to be seeing this f-statistic over and over and over again throughout the course. It's going to be the statistic we're going to use when we compare means, like more than 2 means, 3 means, etc. And we're going to be using this a lot. So please read this. And I just don't want to read it to you. It's just boring for me to read aloud. But I will, let's look at, since some of you are having, especially people who haven't had STAT 100, need some help with the basic idea of hypothesis tests, I think we should read this summary, okay, together. So the basic idea of these, because we're going to keep doing more of these. So all these significance tests are just a statistical check to determine whether some effect you observe in your sample could just be due to the luck of the draw, or whether it's due to a particular cause, evidence of a model that's not just, or whether it's just due to chance variation. That's what you're doing with all these significance tests. So the numerator of the test statistic is a measure of how large the effect is. The bigger the effect, the bigger the correlation coefficient, the more evidence you have that there's a real correlation in your population. And the denominator is a measure of how large the chance error is, right? Look. they all have, that's, it's a sum of squares model over your sum of squares error. That's what it's called. Sum of squares model, it's the ratio of your model to your error. Okay? So, now, Z and T tests can be used when the effect is a single difference, like the difference between male and female test averages. But what if I add another group, like male, female, and transgender? You can't boil it down to a single sign difference, right? So, but as long as you just have one slope, or an observed percent minus an expected, difference between two group averages, then you can boil it down to a single signed number. You can have a directional alternative, and you can do a Z or T test. That's the situation we've been in so far. You can also do a chi-square test for those, but a chi-square test is more general. Same with the F. They're more general. The size of the effect, so you can use these when the size of the effect cannot be expressed as a single difference with a sign. Like you want the difference between three groups. Instead, we're looking at a whole pattern of differences, and we want to know if the whole pattern differs from what we'd expect under the null. In these cases, we have to square a set of differences and combine them. So the positive and negatives don't cancel each other out, and that's why these can never be negative. So we are going to be using these in multiple regression, and when we have more than two differences, more than one single difference between, like treatment and control or something, if we had multiple treatments we wanted to compare. Okay, now for simple regression, we can always square the Z or T stats to make them chi-squared or F. In our next section on multiple regression, we won't be able to use the Z or T stats because we'll have multiple slopes that could be positive or negative, so we'll have to use the chi-square F test. And that's where we're headed. We're leaving simple regression behind after we turn the page. So for all significance tests, the bigger the test stat in absolute value, the smaller the p-value, right? The stronger you have the evidence against the null. And there's two factors that influence this, the significance of the test statistic: the size of your effect and your sample size. The bigger the sample size, the more likely you'll be to get a significant result, and the bigger the effect, the more likely you'll be to get a significant effect. And when you make formulas like this, why I unify it like this is because it's apparent in the formula that the bigger your numerator is, the bigger your sample size, the bigger this test stat's going to be, and the bigger your correlation. And in the denominator is error. Okay, so I like formulas where this meaning, it's very intuitive what's going on there. All right, now let's go to page 53, and we'll finish chapter 12 today. All right. Questions so far, anybody? All right, so this probably looks familiar to you. The size of a negative correlation between your shoe size and how many pairs of shoes you own. Negative correlation, right? We've seen this. This is observational data. And we looked at this back on page 19, I think. Yeah, there it is, page 19. And we saw okay, the confounder is gender because males have bigger feet and they have less shoes. So we said, hey, let's stratify into males and females, and then we'll see that the difference between small feet and big feet goes away. And it's gender driving this negative correlation. Gender is the confounder if you're looking at a causal relationship here. Once you split on gender, it goes away. And so we said there's two ways to control for confounders, right? To control for these. One is stratification, and the other is modeling, including the confounder as an independent variable, a predictor variable, and a regression model. In part 4, which we just entered, we'll look at this example by stratification and modeling, and that's exactly what we're doing. So here we are. that is what we are doing here. All right, so so including a likely confounder as an independent variable, as a predictor in a regression model, is one of the main uses of multiple regression. For now, let's look at this simple case of adding this extra binary variable, binary just two values, male, female, 0, 1, binary variable, to our regression equation. So here's our regression equation without gender. It just says y, the number of shoes, is equal to some intercept, minus 2.154, that's our slope, times x, the shoe size. That's what we have. And we've got this negative correlation that we suspected gender was the likely confounder, right? So we split on gender, and we looked at males and females separately. We can do that. We stratify, and we break it down and separately, and we see that there's basically zero correlation, right? So this is stratification. The big feet and the small feet and the big feet are balanced within each group, even though they're not here. And the picture why that's happening is because, picture this, is because you have two prior groups. This is number of shoes, number of pairs of shoes, and this is shoe size. And the extreme version of this is you have females here and males here with small feet and lots of shoes. And so it gives you this, the overall effect is confounded by prior group membership. When you look at each one separately, like here and here, you get rid of that, and inside each group, it's completely flat or nearly flat. Okay, that's what we see here, nearly flat. That's the picture. So, let's turn the page. So before we go on, we're going to include this binary variable, gender, in the model. So what does it mean to do a regression with a 0, 1 variable? So that's what this is. This is gender here. So this is 0. Males are coded as 0. And here's 1. And females are coded as 1 on this X variable, gender. Sorry, here. So, so that's what we have here, and we get this regression equation. It says the number of pairs of shoes is some intercept plus some slope, and look what the slope is. The slope is this, as you go from 0 to 1, you go up from 6.884, which is the average for males, up to, you add 12.86 to it, and you get up to 19.74, which is the average number of shoes for females. I can show you this data. Okay, let me see. This, I just ran out of batteries here. Shoot. Let me show you this data first. So we'll go to scatter plots. All right, so here's the data that you is in your notebook, and here's our regression line. And this is the equation that you had on the previous page, on page 53. And then we split the plots into males and females, and pretty much you have a flat line. All right, now we want to go back and we want to look at, let's unsplit, and now we want to look at gender predicting shoe size. So males are coded as 0, and females are coded as 1. And if you look at, so if I split it, you just have, okay, the males, it's predicting their average, and the females, this line predicts their average, and you can look at the stats here. So the average number of shoes for guys is 6.884, and for females, it's 19.74. And that's all that regression line is doing. All right, so that's where we're at so far. And let's go back to our document camera. And so we've got this correlation of 0.5082 between we coded women as girls as 1, and they have more shoes. All right, so now what are we doing here? What does the regression equation give for males? So the predicted number of shoes for males would be what? Well, 6.884 plus 12.86. Now, males are coded as 0, so let me write that down here. X is equal to 0 for males, and X is equal to 1 for females. So we have males here, so this is going to be a 0. So we just get 6.884, which is equal to the average for males. That's what I have here. It's just the average, Y bar for males. The average for males. Okay, that's what we have. And what does this equation give for females? It's going to be very simple. It's going to be 6.884 plus 12.86, but now X is what? For females, it's 1. So we add, yes?
So this is saying like this is the amount of average, like amount of shoes that they have?
Yeah,
Okay.
exactly. The men have a lot fewer shoes on the average, and so when we add these two together, we get 19.74, which is the average for women. Okay? So can you see, like when you look at this, because we coded males as 0, this equation is what? Our predicted is what? This 6.884 is what? The average for males plus, what's this 12.86? That's just when we go over, look, it's just how much we have to add to 6.884 to get 19.74. It's the slope. As you go from 0 to 1, you go up by 12.86. It's just the female average minus the male average. So when X is 0, you just get the male average. When X is 1, you get Y bar, you get that. You get the female average. Okay? So it's very simple regression equation. So, but what if we coded females as zeros? What then? Just think about what it would be then. So now we have X equals 0 for females, and X equals 1, which I could have done for males. Then what would happen? Think about it. First, look at the picture. If I put females as 0, they'd be here. So this whole big bar would be here. And males would be here. And we'd have the same line but going down. So we'd have Y bar equals, let's just think about it. We have an intercept plus something times X. So since X is 0 for females, start with females and say when that's 0, you want to predict the, oh, so sorry. I say, so this is your intercept and that's your slope. So I said X is 0 for females, so when that's 0, it looks like this. And you want to predict the average for females. So you'd put 19.74. That would be the equation you'd get. And then what would you put in here? Well, okay, so far we have the average for females plus, now when X is 1, what do I want in here? I want something times X. So I want to end up with the average for males. So that means I have to subtract off the average. I'm sorry, I'm switching between Y's and X's. That's a Y. Sorry. That's a Y. And then those are all y's, and so you have y female minus y female. Okay, so this is obviously, when that's 1, right, I want to end up with, for males, I want to end up with 6.884, so I have to subtract that off, 19.74. And what do I get? So my equation is, that looks ugly. Does that bother you? Raise your hand if it does. It bothers me looking at it, but I think it just looks so bad. I'm sorry. Here, I'm going to make it look pretty now. So you say 19.74 plus, I'm going to subtract those two, and you know what I'm going to get? Just the opposite of this. This is the difference. So I'm going to get plus negative 12.86 times x. That's what it is. Does that make sense to everybody? All right, that's the idea. And now what am I going to do? In the last 10 minutes, now we've got two simple equations. We have gender predicting shoe number, and we have shoe size predicting shoe number. And let's put them together. And that's multiple regression. All right, now we have two simple regression equations. One predicting shoe number from gender, and one from shoe size. Here they are. And let's combine the predictors into one multiple regression model, and this serves almost the same purpose, not quite, as stratification. It allows us to separate out the effects of each variable. So, what do we have here? This one I said is gender. I put that one first, 0, 1, and this one shoe size. And what each one does, you know what this is? It controls for the other variable. This is what multiple regression always does. So this slope for gender, what does it do? It says it estimates the difference gender makes in the predicted number of shoes for those with the same shoe size. So for women, for example, who have size 10 like I do, and men, what's the difference on the average? We all have size 10. This slope for gender tells us the difference. And that's a big effect for gender. Now, what is the slope for shoe size? That's controlling, that estimates how much an increase in shoe size, for like going from 9 to 10, for those of the same gender. So that's that one. What's that? That's what that's going to do. Now here it looked pretty big because it was confounded with gender. But when we separate out the effects, we get a whole new equation, and that's going to be pretty small. And here's our new equation. And see how that went down to almost nothing? Because that shoe size for people of the same gender, that's a pretty flat line. And that's not even significant. These are our slopes. This is the analysis of variance printout. And these are our slopes right here. This is like beta 0, B0, B1, and B2, right? And here they are. And this one isn't even significant. Look at it. Not significant. It's tiny and not significant, whereas this one is hugely significant. Look at that low for gender. It's a big effect. Big effect. It's about, as you go from male to female, it's about a difference of 13 pairs of shoes. And so this is very significant. Okay? So, only gender is significant. Shoe size hardly matters, and that's what we saw when we stratified. And that's what you're getting in this model. So, let's look at this, and let's interpret it. What does the above multiple regression simplify for males and for females? Well, for males, let's look at males. And males is when I coded it so that x is equal to 0 for males. So we're just going to say the number of shoes, y, is equal to 4.255 plus 13.51 times 0. So x1 is 0. That. Plus a tiny little insignificant effect of 0.2472 times your shoe size, which is x2. And for females, now we have x1 equals 1. So now we're going to have 4.255 plus, we're going to add this 13.51 in. That's how many more, that's the effect for being a female. Look how many more shoes you have. Plus this tiny little effect. It's not significant. So what multiple regression does is it forces you to have the same slope. So let's look at this. Until we put an interaction term in, multiple regression forces the same slopes. And they're not quite the same. So let me show you what I mean. So let's go to our computer. And when we were doing shoe size and shoe number, and we split, they're not quite the same. Look, if I combine them into one plot, you see there's a slight difference between the slopes. And these purple dots are all girls. These are all boys. This is the boy line. See, they don't quite have what multiple regression does without an interaction term is it forces them to have the same slope. So these are the two equations you got. Exactly those two equations, which aren't really the same thing you do if you get stratification. With stratification, you're going to get more information. We'd have to include an interaction term to get exactly the stratified effect. Now, while we're here, let's look at our own data. We haven't done that. We haven't had any fun with it. So let's look at our own. And I was just doing this with the other class. And this is you guys' data right. How come I can't find it? Oh, here it is. Stat 200 Survey 1. Look at this. Okay, so here we have shoe size predicting pairs of shoes. And we have this negative effect here. Here's your regression. But look at what I discovered. Somebody's lying in our class. Look at this. Last class I saw this. This person says they have a size 4 and 0 shoes. Now that could be possible. Could be possible that somebody in the class has 0 shoes. It's happened before. But, because I had somebody who had 0 legs once. But this is, how do I know that this person's lying? Watch. And this is fun to do. This is an outlier. So let's see if it's real or not. So I'm going to go to display and modify data. This person is right here. 0 pairs of shoes. Right there. Let's see what else this person. They said female. Identify as, what is that, trans? Height is 89 inches. 89 inches? That's unbelievably tall. 297 pounds in a size 4 shoe. A female? That's 6'9", right? What does this say? Study 0 has a 1.0 GPA. ACT of 15, 30 pets, 12 siblings, $120,000, sleeps 12 hours a day, and 0 pairs of shoes. I think that person, let's do an eye clicker, okay, on this one. So let's go back to, take out your eye clickers. And let's go back to our scatter plots. And I want you to, okay, shoe size, shoe number. What do you think is going to happen to R if I delete this point? So I'm going to start this going. So you're going to vote. Do you think the line is, do you think this is going to get bigger in absolute value? Have a stronger negative effect? A, if you think that. So if we're going to have a if I take away this point, do you think the line's going to get steeper down? Going to have a stronger negative effect? Or B, do you think it's going to get flatter? So that correlation will go away. So vote. I delete that point, and I'm going to delete it. You can delete the points and see what happens. So are y'all voting? If you think it's going to go, I'm going to delete this, and do you think that's going to make a stronger negative effect? Like this will go closer to negative 0.3, or it will go closer to negative 0.20? Is B. You can't, it's just for answering. So just answer. Has everybody answered? Okay, let's see what you think. I'm going to stop it. And yes, it's going to get stronger. Watch. 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 If I delete this, watch what happens to this. See? Now let's look at this. Let's see when we split. Let's split the plots. Oh, that person's still here. You see, we have this positive slope now. Positive. See, it's pretty strong. Let's another clicker question. Okay. So now I'm going to delete this point again. Do you think the line's going to get flatter? That will be, A will be flatter. It's going to go, see how this point is pulling this part down? So do you think it's going to get flatter? That's A. Or B, do you think it's going to get steeper when I pull that? You see, look, we have a correlation here for girls because of this point. This person who's lying dragged this down. So when I delete this, don't you think, guys, vote for A? Don't you think it's going to get flat? I'm going to do it, and then you can still vote. I want you to see. See how it got flatter? That got less? All right. So now let's just see what you voted. People aren't listening probably, so I bet there'll still be some people who are going to choose B, which is wrong. Choose A. Let's see if we can get 100%. No. No! No, you perverse people! Go home. Bye.